Yes, I would also like to start by thanking the organizers for this wonderful conference. I'm very delighted to be here. So I would like to tell you about some progress we made with the goal to make a brain interface with a visual brain for people who are blind. And I start with a disclosure. I'm a co-founder of a company, and the reason is that we actually want to go all the way. And so some of the work to really make a device that goes into patients implies that you have to go through all kinds of regulatory processes, really making a product which goes a little bit beyond the normal academic work. So in the world, there are about 40 million people who are legally blind, and many of them, of course, have severe problems in everyday life, taking care of themselves, going to the bathroom in an unknown place. And their number is increasing because of, at least in the Western world, the aging of the population. So this shows you how the information goes from the eye through the optic nerve to the LGN, a region in the thalamus, then to the primary visual cortex at the back of the brain. In most people who are blind, the problem is in the retina, and in many of the cases, the majority, it happens during a later age. So when the visual system has been fully developed, it's just the input that is then missing. And in many of the cases, most of the cases, actually, the fibers in the optic nerve, they come from the retinal ganglion cells. The retinal ganglion cells are damaged, so there are no fibers anymore. So in these cases, it doesn't make any sense to put a chip in the retina because these signals will not arrive in the brain. So that's why you have to look higher up in the system, in the LGN or visual cortex. So we've been focusing on visual cortex, and we are not the first. So brief historical note. So Giles Brindley, already in the 60s, built a system to restore vision in blind people. What you see here is an X-ray, and all these white rectangles are actually mini coils. They were implanted on the skull under the skin. So he was already thinking of a wireless system, creating a wireless system. And you see this small thread on the back, that is a set of wires that then run to an electrode on the top of the visual cortex. So this was surface stimulation. And this is Giles at work. And you see the blind subject, you see these small black rings. That is the coil on the other side of the skin that kind of gave rise to the induction. He uses AC currents here. So quite remarkable that he was already in the 60s doing this. Now, it's more than 50 years later, and the technologies, of course, have hugely improved. And we think that this could be really the right time to bring this technology into reality. So the idea is the following. Actually, we are now working with penetrating electrodes that are really sitting between the brain cells. And one of the reasons is that with surface electrodes, you have to pass a lot of current, typically milliamps, whereas if you have an electrode in the brain, it's only microamps, so it's 100 times less current. And it allows you to produce more precise perceptions. So these perceptions that you create, we're now using these Utah electrode arrays. I will say a few more words about that. It might not be the technique that gives you sufficient longevity, but if you put an electrode in the brain, primary visual cortex here in purple, and you stimulate it, then a person, it can also be a person who has been blind for several years, will perceive a dot of light, and that's what we call a phosphene. Now, as we all know, primary visual cortex has a whole map of space, right? So if you then position the electrode slightly at a different location, then the person will perceive a dot of light at a different location. And if you implant 1,000 electrodes or more, you could in principle create 1,000 different phosphenes at different spatial locations. And you can now work with it like a scoreboard or a matrix board that you know from the stadium or from the highway. If you flash one bulb, you will see a dot of light. But of course, you can create a pattern by stimulating multiple electrodes at the same time, right? So that is the reasoning behind while this would give rise to quite a rich percept, and you can use it to display many different things in the user's perception. So this is what such a system might look like in the future. So the user would wear a camera, can be embedded in glasses. You can buy those, nothing to be developed here. And then you see in the upper left a picture from a street scene. Now this is too much information. You will not be able to give rise to such a rich visual percept. So you have to do something to simplify it. For that, you can use artificial intelligence. So in the lower left panel, you see the outlines of vehicles, pedestrians, and cyclists who might be very useful to know about if you're navigating the scene. And that type of complexity can be actually conveyed to a cortical prosthesis, we think. And then, of course, you need to have something that is wireless. So wireless information and power transfer, maybe a brain chip, and these brain chips then make sure that the current goes to the appropriate electrode so that you perceive what is shown in the lower left corner. Now, what had not been shown is that it's possible to really convey shape perception by pattern stimulation of the visual cortex. So that's what we set out to do in a study that was published a few years ago, and this is mainly the work of Xing Chen. So what we did is we implanted, of these Utah electrode arrays, we implanted 16 of them. Each of the arrays had 64 electrodes. And this is what it looked like. So you see these black squares sticking out at the top. These are the Utah arrays. You look at them from the back. These wires are actually bundles of gold wires that make an electrical connection to this pedestal, which is a transcutaneous connector. So that is protruding through the skin. And these flaps of gray metal is actually titanium that is screwed onto the skull of the monkey. So it's the connector that protrudes through the skin, and through that you can make the electrical connection. So this is how we implanted the electrodes. So every square is one of these Utah arrays. You see that we positioned 14 of them in primary visual cortex. So, and 2 of them, that is sort of in the upper left of the schematic, are in area V4, which is a higher visual area. And what we then do, and I'll show you how we do it, is map out the receptive fields, because these monkeys are not blind, so we can present visual stimuli and work out where the receptive fields are. And you see that there's a very nice mapping actually from the arrays to how the receptive fields are positioned in the visual field. So the center of this bullseye is the center of vision, so that's the fovea. And you see that these red receptive fields, that they correspond to the electrode array that's shown in red, and then you see a very nice systematic mapping of all these electrode arrays that then convert into receptive fields in a very systematic manner. So all the receptive fields here are in the lower right quadrant of the visual field. That is the part of the primary visual cortex that we have easily access to. And we replicated the effects in a second monkey. So the results were quite similar. Now I'm going to show you how we map these receptive fields. So this is a mock-up. So this shows you the monkey sitting in the setup. He's looking at a red dot at the screen. Of course, you don't see these electrode arrays in reality. They're under the skin. But here we map the activity onto the brain, and you see that this moving white bar gives rise to a wave of activity that propagates across the array, because these receptive fields are touched one by one by this moving light bar. And this is basically how we can work out the receptive fields of all these neurons are. You can also do the same mapping and now map it out into the visual field. So now we're showing the activity at the place in the outside visual world where the receptive fields are. This is actually slowed down by a factor of 5, and you see that there is a wave of activity that trails the light bar, and the delay between the activity and the light bar is actually the time it takes for visual information to go from the retina to primary visual cortex. It's about 40 milliseconds. Okay, so now we know where the receptive fields are, so we can start stimulating. And here we're stimulating one of these electrodes at any one time. So these green circles are the sensors of the receptive fields, and the white circle is the receptive field that belongs to the electrode that we're stimulating. And you see that we can do this, and the monkey makes an eye movement. He's been trained to make an eye movement to where he perceives something. That's the purple dot is where he's positioning his gaze. He starts the trial by looking in the center of the screen. And you see that roughly he always goes to the position of the receptive field of the electrode we're stimulating. And this had been shown before. Maybe we're the first to be able to do this for hundreds of electrodes. And so it basically means that the percept will indeed occur at the receptive field of the neurons you're stimulating. Now, the big question that had been unanswered is, what now about pattern stimulation? Can you really convey more complicated perceptions directly onto the brain? Now, to find that out, we trained the monkeys. As I said before, they were not blind, so they could just see patterns. So they're looking at a central dot. Then we present a letter, And we trained the monkeys to recognize 16 letters. And then after the sample, there was a choice menu with 4 letters here, and it was the task of the monkey to pick out the letter he just saw. And this was all done visually. And then in the exciting part of the experiment, we did not present the sample visually, but we tried to paint it directly onto the cortex by stimulating the set of neurons whose receptor fields jointly would form the shape of a letter here, the letter A, hoping that the monkey would make an eye movement to the appropriate letter. And that worked, as you can see here. So now we're stimulating multiple electrodes here in the shape of a letter O. And you see that the monkey indeed makes an eye movement to the appropriate letter. Here we're stimulating an L. So that made us very excited. So this was really, we thought it was mind-boggling that you can really paint such structured information onto the visual cortex by stimulating multiple electrodes at the same time. I think the monkey makes an error here. So it's real data. Okay, so that was really cool. So now one big question with this technology, suppose you want to implant 1,000 electrodes or even more. We know from previous study and also in our own work that some electrodes give rise to perceptions with very small currents. Say 10 micrograms might be enough. But other electrodes require more current. You might need to have 100 micrograms or even more. And if you have 1,000 electrodes, you can ask the subject, of course, to calibrate. So that's what you see here in the graph. If you give, for this particular electrode, if you give less than 10 micrograms, the monkey doesn't perceive it. If you give more than 50 micrograms, the monkey always perceives it. But for the next electrode, this threshold could be 100 micrograms. If you want to do this manual calibration, you might spend 20 seconds or even a minute to calibrate it, one electrode. And if you do that times 1,000, it becomes infeasible, right? The patient would be spending hours and hours calibrating the electrode, having maybe even little time to really use the prosthesis device. Okay, so we thought it might be interesting then to record in V4, which is the next one of the next higher areas, while we're stimulating in V1. And this shows you the response of V4 neurons while we're stimulating a V1 electrode. This is actually electrode for which the behavior is shown in the upper left. And you see that if we give small currents, so 7 or 9 micrograms, we don't elicit any response in area V4. But once we start eliciting a response in V4 after 10 micrograms or more, then actually that corresponds to the threshold of perception. So the moment you start activating the neurons in area V4, that's also the moment that your current is strong enough for the monkey to perceive the microstimulation. Well, that's good news, because if you can then read out in V4 whether the V1 stimulation is strong enough, this could be done offline, right? The patient could be doing something entirely different that could even be done during sleep. He could calibrate the system, and it does not require a lot of time of the patient. So making it more feasible to be able to use effectively 1,000 electrodes or more. So we think that this is looking promising. So we think that maybe in 1 or 2 years, we will be able to have a system that can be safely used in humans. But it's also good to know that we work together with a group in Spain led by Professor Eduardo Fernandez, who is already using Utah arrays in the visual cortex of a human subject. And this is a subject that can be named. Her name is Bernadetta Gomez. She's very famous now in Spain. And she was a blind volunteer in his clinical first-in-human trial. And she received a single Utah electrode array in primary visual cortex. So this shows you, it's a bit small, but you see this in panel A, you see this white square, and then in the middle is a green square, and that's where the array was. And it was placed in primary visual cortex. And in panel B, you see, looking basically on the back of the array, where you see these almost 100 electrodes. Now, when they stimulated a set of electrodes simultaneously in the shape of a large square, she saw a large letter O. So that's kind of very good news. When they stimulated a small square, she saw a small letter O. So that seemed to be confirming the data that we obtained in the monkeys. But it was not always as clear. So this shows you an example of a pattern where she clearly indicated seeing a letter I. Well, perhaps. But here, she saw the letter L. and I didn't see it. So we think what's going on here, this is a single UTA array, so it's 4 by 4 millimeters. And these electrodes that are somewhat separated might actually also cause unintentional activation of neural tissue in between. And we think that that is the reason that she might have seen a letter L, which was not intended. And I think the difference between this study and the monkey study I was talking about before is that here all the electrodes are in the region of 4 by 4 millimeters, whereas in the monkey they were distributed across at least more than 2 centimeters of cortex. So I think if the electrodes are nearby, then you might expect these interference patterns. If the electrodes are farther apart, then you probably get more independent percepts, and the matrix board analogy works better. So this is Bernadetta talking about the experiences.
Yo estaba pletórica y bueno, y todo el equipo también, entonces claro, os decía, pues estoy viendo un punto luminoso y todo el mundo callado. Chicos, ¿qué os estoy diciendo? Que estoy viendo un punto. Y bueno, nada, al final pues fue una explosión de alegría y todos ahí contentísimos. Pero por supuesto que si ahora hubiese uno que fuese inalámbrico, que se pudiera trabajar con mucho más electrodos y se pudiera ver más, yo ya no pido una visión, simplemente distinguir una puerta, un obstáculo, lo volvería a hacer, sí, sin duda alguna, sí.
So for me, she's a real hero because he realizes that he's participating in a human experiment. So the UTA array had to be explanted, so she had to go to 2 times the brain surgery after 6 months. And of course, she's doing this because she wants to make the technology available for blind people in the future. I think that's quite remarkable. Now, I would like to highlight 2 of the problems with this approach, and we are actively working to solve those problems. So in a blind person, it's not so super easy to localize the phosphine. So the task that you're using is you do a microstimulation and you ask her to touch on a tablet the position where she's perceiving this phosphine. And because there's a single UTA array of 4 by 4 millimeters, and the primary visual cortex, you should realize, it's 25 square centimeters on the right and another 25 square centimeters on the left. So you're covering less than 1% of the visual field. The visual field in humans is 90 degrees on both sides, 70 degrees up and down. And with 1 UTA array, you're covering this position that is a red ellipse as if she's looking through a very long tube. So that's one problem. So that's something that we need to solve. And so one approach that has actually been proposed by John Pesaris is not going to the primary visual cortex because this 25 square centimeters is also folded into a sulcus. But to go to the LGN, where you have the entire visual field representation in a small volume of about 120 cubic millimeters. And the other problem is actually gliosis. So what you see here is the result of this implantation that we did of 16 UTA arrays. And this is, the monkeys were sacrificed after 3.5 years. And you see that we created a large lesion, sort of a big hole in the brain. And we believe that the reason is that these 16 UTA arrays, they're also tethered with 16 cable bundles, and the monkey might be moving every now and then. Of course, this implant is not moving with the brain. And as a result of this, the monkey also actually lost vision. So these black contours are actually the aggregate receptive fields of all the neurons we recorded from. And in yellow, that's the part of the visual field where the monkey is quite able to detect small dots, but in the blue regions, there is a deficit, right? So instead of improving vision, we are actually degrading vision. So that is definitely something that also needs to be solved. Here you see the gliosis response. So you see a couple of these UTA arrays when explanted, and you see that the electrodes were fully covered with fibrous tissue. Now, one way out are these new flexible polymers that are now being developed for recording and also for brain stimulation. So we're working together with Zhongxia, but there are other groups in the world who are developing this. So it's called polyimide. It looks a little bit like kitchen foil. So it's super, super flexible. It can be made very thin, 10 microns, even 1 micron. And it floats between the brain cells. And it does not seem to cause a large gliosis response. So I think that's a very promising technique. And here This is an experiment from our own lab in which we worked together with people in IMTech at Freiburg who created also these flexible electrodes, and we implanted it in a mouse. And for more than a year, we were able to have the mouse report when his primary visual cortex was being stimulated with very low thresholds. So in this example electrode, the thresholds was only 3 microamps, and on average it's about 8 microamps, which is, I think, 3 orders of magnitude less than if you do surface stimulation, and which has been done a lot in human patients. Okay, and so I think also combining that with the LGN, it might be possible to get quite a reasonable coverage of the visual field. Now here you get an impression of what prosthetic vision in the future might look like. So I try to see what is there. Do you recognize it? So it is recognizable, but it's not superb, right? So I think that we have to be realistic. If you have only 1,000 electrodes, or maybe we go up to 5,000 or 10,000 electrodes, what you're going to perceive is quite rudimentary. But also, if you talk to blind potential future users, they would tell you, many of them, that it would make a big difference still, because that would perhaps allow them to navigate more independently, and also to judge the facial expressions when they talk to people, which is also something that they really miss in social interaction. Okay, now I would like to close with a sort of more ethical consideration of what you're doing when you're electrically stimulating the brain. So if we're electrically stimulating primary visual cortex or the LGN or even the retina, we're trying to kind of reactivate these sensory surfaces that are normally, of course, giving very useful information. And we know from our own work and also from other work that you can decide to attend. So if you have a pattern stimulation, you can decide to attend to some of the phosphines, maybe not to the other phosphines, so you kind of keep control. Then you might consider to go to higher areas like inferior temporal cortex, where you find neurons that are, for instance, coding for specific shapes. We heard about it yesterday. And you might thereby enrich the percept, right? But one thing that I'm not entirely sure about, how much control does the subject keep over his or her own interpretation? So we know from work of Nancy Kenwisher, for example, that if you stimulate some neurons in this brain region, you could actually impose the perception of something, say the perception of a face that is imposed on a basketball, or that is imposed on a cardboard box. So maybe you have less control if you stimulate higher visual areas. If you stimulate parietal cortex electrically, certainly if you talk about pattern stimulation, we know from beautiful work of the lab of Winrich Freiwald that you can actually influence where the monkey directs his attention. So you can emphasize some parts of the visual scene over other parts of the visual scene. So of course, there you're already kind of taking over some of the control, maybe of the future user. And if you're doing pattern stimulation of the frontal lobe, I'm not talking about relatively coarse brain stimulation of these structures, because I don't think you have so much influence on exactly, well, maybe exaggerating some patterns and suppressing other patterns. But if you do pattern stimulation of the frontal cortex, maybe that's really where you're creating thoughts and creating intentions. So I think there, the issue of control becomes very important. With that, we'd like to close, but not before mentioning the people who did the work. So the monkey work was done by Sting Chen and Feng Wang. Antonio Lozano and Eduardo Fernandez, they did the human work. The polyimide work was done by Bing Li and Doreen Orleman. And Stein did the simulations I showed. And I would also like to mention the collaboration we have with people who create these polyimide probes. And the probes I was talking about were made at IMTech by Maria Asplund and Christian Buller. And these are the funders. Thank you for your attention.